So in this video we will be learning the thermal model of motor for heating and cooling derivation. Okay, so here why we are going this, first what all statements you have to write. So basically you need to remember this many statements. Okay, so what is this actually? See, basically in any motor or the machine, heat flow and temperature rise will be there. Okay, so prediction of that we have to do, right? Prediction of that, so that is very difficult in any electric motor. Okay, so why it is difficult? Because of its complex geometrical shapes as well as the use of heterogeneous materials. So because of the two factors, it is very difficult for the heat flow and temperature rise prediction. So what we are going to do, we are going to consider the thermal model of the simple thermal model of the machine that can be obtained by assuming the machine to be homogeneous body. Okay, we are assuming the machine to be what? Homogeneous body. So let us start the derivation. So starting with the first point of derivation, so we have to write that let us assume, let the machine be what? Homogeneous body. And we have to consider many cooling parameters for that. So cooling medium parameters we have to consider. So what all the parameters is there in this? Let us try to see. See, the first one we are considering the P1. Okay, small letter P1. So it is nothing but the heat developed in the system, and it is given by the joules per second, or we can consider as watts. Okay, next P2 is nothing but heat dissipated. Okay, so P1 is heat developed, this is heat dissipated to the cooling medium, and it is joules per second, the units. Next, capital letter W is nothing but the weight of the active parts of the machine in kgs. Small letter H is nothing but the specific heat, and the unit is given joules per kg per degree Celsius. Capital A is nothing but the cooling surface, and it is given meter square. Yes, area will be in meter square. And D, small letter D, it is something but the coefficient of heat transfer. Okay, then theta is something but the mean temperature rise, degree Celsius. So these are all the parameters. So total 7 parameters. Okay, so remember like this is derivation. Remember like this, point wise you remember. So first point, we are considering the machine to be homogeneous and the cooling parameters as follows. Next, what we are going to do now, the second step, nothing but during a time increment, that is dt. So let the machine temperature rise be d theta. Okay, temperature rise, theta is nothing but mean temperature rise. Okay, so we are considering the second step, it is nothing but the during time increment dt, and the machine temperature rise be what? The d theta. Now since it is there, so in a system what happens, heat absorbed, this is very important, heat absorbed so this is very important. Now what is here? Second point, we have heat absorbed in the machine. Okay, in the system we have is equal to what? Heat developed inside the machine minus heat dissipated to the surrounding cooling medium. This you have to remember. Okay, so how much our heat is absorbed in the machine will be equal to heat developed inside the machine minus the heat dissipated to the cooling medium, and it is given by WH d theta equal to P1 dt minus P2 dt. That means this part is the heat absorbed, this is the heat developed in the machine minus heat dissipated to the cooling medium. P1, P2, all the parameters we have discussed. Okay, cooling parameters. cooling medium parameters. Now this was the second step in which we found out the first formula. Going further, here we have to consider P2 to be what? Theta dA. Theta dA. So P2 you have to replace with theta dA. So I'll substitute the second one. I'll substitute the second equation in 1. Okay, substituting here. So this will become WH d theta is equal to P1 dt minus P2. In place of P2 it will be theta dA dt. Okay. Next, now here WH I'll write it as what? C. So I am replacing C, so I can rewrite. We have to just rewrite this equation. How will you rewrite this equation? Now one more thing you can do, you have to just divide. This is derivation, okay, remember stepwise. So you have to just divide by dt. So what will happen when you divide by dt? No need to show the division part, you just say that substitute in 2 in 1 and rearranging the terms. So this will become c d theta by dt equal to P1 minus theta dA. That's all. Correct? Why? Because see, I'll just show you here what happened. So WH d theta, I said to divide it by dt is equal to P1 by dt, and P1 is, sorry, dt is here, minus theta dA dt by dt. So whole thing divided by dt. Now here dt get cancelled, here also dt get cancelled, so remaining part is this one. Now WH I have replaced with C, so I can write it as where C is nothing but equal to WH. Now what is the meaning of C here? C is the thermal capacity. You have to denote all these things, okay? Thermal capacity of machine, which will be in watts per degree Celsius. Now next, I'll replace one more thing, theta dA. Here dA I'll replace it with what? Capital D. Okay, so our equation becomes c d theta by dt equal to P1 minus d theta. So where I can say that D is equal to dA. Now what is D? D is nothing, capital D is nothing but the heat dissipation constant. Heat dissipation constant. Okay, so this all terms you have to write. So this dividing by this thing you can just avoid it. No need to show that thing. This is just derivation, you can directly write. Okay. Now this equation is very important. Mark it as the third equation. Now after finding this equation, third step, we'll go for third step. Bring this C to right hand side and rearrange the equation. Okay, so rearrange the third equation. So what will happen? D theta by dt. So C I'll take it to that side. P1 by C minus d theta by C. Now here this theta is there. Theta I'll keep it on one side like terms. So it will be d theta by dt minus will become plus d theta by C is equal to P1 by C. So why am I writing like this? We are going to compare it with what? Differential equation. Okay. Now here what will happen? So comparing it with differential equation, you need to understand, so which is given by, you might have studied, dy by dx is equal to dy by dx plus p of xy is equal to q of x. Okay, so this is what we had to do. Okay, so dy by dx is equal to p of xy equal to q of x. Now in order to solve this first order differential equation, we have what all methods we have. We are going to use the integrating factor method. So in that, what you have to do, y of integrating factor is equal to integral of q of integrating factor into dx plus the integrating constant k. This is what we have to do. Now this is for the general equation. Now we have to do it for which one? This equation. So for this I need to find out what integral factor, which is equal to e power p dx. Okay, so here we have to do e power, what is p here? P, compare this with this. What is p? P here is nothing but d by c, right? D by c. P of x, we can say p of x, it is nothing but d by c. Integral of d by c dt, here always dt with respect to dt only will come. It is equal to e power c d by c into t. Here I can just rewrite it this one as e power t by tau, where what is this tau then? Where tau is equal to c by d. Okay, tau is nothing but c by d. Now is tau is just, we can call it as, this is the new variable, it is nothing but the heating constant. It is nothing but the heating constant for the heating equation. Here we have two equations, heating as well as cooling. So you can write it as heating constant or the cooling constant. Okay, so tau is nothing but c by d. So it is c, this you can, one more step if you want you can include, it is nothing but e power t by c by d. Okay, that is equal to this one. So we got integrating factor. Now we have to substitute in this equation. So that is nothing but y of integrating factor, which is nothing but e power t by tau. This is only the integrating factor. Okay, t by tau is equal to integral of q of integrating factor. What is q here? Q you have to compare, right? P we got it as what? D by c. Okay, after comparison, q we are getting it as what? P1 by c. P1 by c. How? Compare this with this. Here q of x, here also q of x. Comparison. Okay, so integral of q of this thing, right? So q means p1 by c into integrating factor e power t by tau plus the integrating constant k. Okay, now here one more thing, here instead of y what you have to write? Y is nothing but theta. Y is nothing but what? Theta. So instead of y you can just write it as what? Theta. So theta e power t by tau is equal to integral of this thing will be p1 by c e power t by tau by 1 by tau plus k. Okay, now theta this thing I can write it as theta itself. Now one more thing you remember, in derivation you know the last answer, right? So the last answer will be in the form of theta is equal to theta ss plus k e power minus t by tau. Yeah, this is the last answer, where theta ss is nothing but p1 by d and tau you already know it is c by d. Okay, so theta ss, so this form you observe here, theta we got, correct? Theta we got, we need theta ss, that means p1 by d we need, correct? And this term we should have, so k is already there, we want e power minus t by 2, so I can just write this as p1 by c into c by d. Why am I doing c by d? So that c and c get cancelled, the left out term will be p1 by d. Okay, plus k e power minus t by tau. Now each and every step no need to explain, from this directly you can write this step. So the final answer will be theta is equal to p1 by d plus k e power minus t by 2 tau. Okay, so this thing you remember, this is the final expression you have to get, this is what you have to obtain. So in derivation you already know the answer, you have to just derive and show. So p1 by d I can just write it as theta is equal to theta ss plus k e power minus t by tau. This is my final equation, and where you can write it as where theta ss is equal to p1 by d. And what is theta ss? Theta ss you can mention it as the steady state temperature. Steady state temperature of machine, steady state temperature of the machine. And one more thing, tau is equal to, a tau is the heating constant, it is equal to C by D. So this is the thing we can write. So it's the final expression. Now we have to divide this expression into two categories, heating and cooling. Okay, first heating will happen, then machine will go for the operation of cooling. Cooling operation will happen, so two temperatures will be there, right? So that time taken for this cooling and heating, that you have to find out equation. So I'll equation, so what here, initial condition I'll apply. So after getting this equation, initial condition I'll apply. Initial condition. Now what is initial condition over here? Here t is equal to 0. That is the initial condition. What will happen when t equal to 0? Theta is equal to theta ss plus k e power, this will become 0, right? T is 0. So e power 0. E power 0 means nothing but 1. So I can just remove this part. So this is what I got. From this k I can take it outside. K is equal to, not outside, k is equal to what will happen? Theta minus theta ss, right? Just bring this side. So theta is equal to theta ss. This thing I can name it as the fifth equation. This, sorry, not fifth. This I can name it as fifth equation. This will be 6. This sixth equation I'll put it over here. So what will happen? Theta is equal to theta ss plus, in place of k it will be theta minus theta ss e power minus t by tau. So this I can expand. It will be theta ss plus theta e power minus t by tau minus theta ss e power minus t by tau. So it is equal to theta ss, I can take common. Inside it will be 1 minus e power minus t by tau plus theta e power minus t by tau, that is equal to theta. Now this theta and this theta is same. So in order to differentiate, what I'll put, I'll convert this equation into two categories. Before that I want to show you one more thing. So this you would name it as seventh equation. Okay, so we'll consider one more condition, that is nothing but the steady state condition. In steady state condition, what happens? T value should be infinite. So t value, when it is infinite, this entire k term becomes 0. Okay, so what will happen? Theta is equal to theta ss plus, from equation 5. Okay, from equation 5, okay, this k e power minus t by tau, this entire term will become what? 0. So theta is equal to theta ss. This is what a steady state condition. Now coming back, this also you have to mention. Okay, steady state condition. So this is the initial condition in which we got the seventh equation. So now this seventh equation you have to observe carefully. Okay, this will divide into two parts, heating as well as cooling. So heating part will be theta is equal to theta ss into 1 minus e power minus t by tau plus, instead of theta I'll put it as theta 1 for heating, e power minus t by tau. This is for the heating. Now for cooling, what happens? Theta is equal to theta ss into 1 minus e power minus t by tau plus theta 2 e power minus t by tau. Okay, so this is the equation for both the cases. Now you have to draw one graph also, that is the final part of the derivation. Heating and cooling curve, we can call it as that. It is between theta and theta versus time. Okay, mean temperature rise versus the time. So you go like this, then it will decrease. So this is the cooling curve and this is the heating part. Okay, 0. So this is the heating and cooling curve. This is the last part of the derivation. So this is what you have to do. Now I'll just briefly explain you what all things happened. Now first step, you have to consider the machine to be homogeneous body. Okay, and the cooling parameters you have to consider, that is nothing but 7 parameters are there, like that you remember each and every term, very important, remember theta and all. Okay, second step is nothing but you have to consider the increment time dt, as well as the mean temperature rise to be theta d theta. This is important. Now this is the form general equation, that is heat observed in the system will be equal to heat developed inside the system minus heat dissipated to the cooling medium. We have to heat dissipate. So that equation, this is the first and foremost equation you have to write. Wh d theta is equal to p1 dt minus p2 dt, where p2 is nothing but theta dA. So you have to substitute in first equation and rearrange the terms. Just divided by d theta, sorry, divided by dt. Okay, no need to show that part dividing and all. Then you will get this one. Then where you have to mention each and every term, whenever you are replacing some term with some other variable, you have to mention. For example, what is c, you have to mention what is c. Okay, it is the thermal capacity of the machine. Then after that I replaced d with da, that also you have to mention what is that. Then after that you have to rearrange, and next step is most important step, where you have to compare it with the first order differential equation. Okay, comparison with that integrating factor you have to find out, put it in this equation. This is the equation. In that y, what is y is nothing but theta, correct. Integrating factor we found out, it is this one, correct. Then q we know, we have to just compare it. Okay, I have written this part here, I have written this part here. Okay, so comparison. So after that you will get this equation. Now one more thing, you already know the answer of this derivation. Remember this, you already know this answer. You have to just somehow get the value of this equation you have to get. After getting this equation, first find out initial condition, then in between you mention in steady state condition where t is equal to infinite, here t is equal to 0, and find out one equation. Then divide that equation into cooling as well as heating part. Then just difference is basically in this theta 1 and theta 2. Heating and cooling curve is important, you have to just specify that also. This is a whole complete derivation.